whole world at our feet, watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see
and welcome to another of my live streams, and let's see if it actually works. It should work. So yes, welcome everyone, and we will be doing the same thing we've been doing every live stream for a couple of last live streams, as in actually solving CTF tasks. So today's is, well, the fourth part of the picoCTF 2019 challenges. We have solved quite a lot of challenges already, and from what I know, there are quite a lot of challenges remaining, so, well, I do expect more parts to be there because I want to solve all and basically each and every challenge that there is in picoCTF. Cool. So today's moderator is Foxtrot Charlie. You can see his nickname right here. And if you have any questions, you actually have to write to Foxtrot Charlie, not to me. You have to, use @Foxtrot Charlie on YouTube or on Discord. Or if you're on our IRC chat, you can just write !Q and then the question, and that works also, but it only works on IRC from what I remember. So there's that, and yeah, this is actually the last live stream of the year. There will be no more live streams in December, so enjoy. And let's see, what do I have here? As usual, some really fast news. Well, news is a bad word. I guess Foxtrot Charlie's website. Thank you, Foxtrot, for being here, for being the moderator again. Paged Out, as you know, is out, and you can download the third version of the PDF. More to come. I'm terrible at drawing arrows. No, this is totally what I meant to do. Anyway, so if you haven't read it yet, for some reason, enjoy. The new version is slightly improved. We uploaded it yesterday or 2 days ago, but there will be even more builds basically before we reach beta 3 and then beta 3 and the final version. So yeah, we still have some stuff to do on that front. But yeah, you already have like 2 issues to enjoy, but if you are looking for more, how about writing an article for us? And to write an article, you have to get it ready by the 20/02/2020, meaning 20 February of next year. So we're still over 2 months, almost 3 months, I guess, to go. And you will find all the information how to write an article in these 2 sections. So there's that. If you already sent us an article and you didn't get a reply, I apologize for that. You will get a reply soon, but the review process will actually start late January or like middle to late January. So yeah, we still need to reorganize some approaches to reviewing process. And I think that's all I have. So we can get right to this. Unless there are some questions. I see there is one question from Liam. Actually, let me show you the questions. You will see the questions right there. Or actually, if we switch here, you will see the questions here. So Liam is asking, will I be at the Chaos Communication Congress? No. Yeah, I never get to go there because the dates are pretty terrible for me. So yeah, especially, I do not live in the country where my family lives, so there's a lot of traveling usually involved, and I cannot really squeeze in another country to visit at that time, so I don't think I will ever see CCC, but I do expect to play the CCC CTF, which is, the worthy CTF season final, basically. Okay. Keshav writes, did you fix the sticker bug in animation? I did. At least I hope I did. It doesn't crash anymore, and I did change it a little bit, so it should work now. I hope. Yeah. It still will not display the sticker though, since I don't have an idea how to display the sticker. As in, I didn't see it in the metadata, like any image information for the sticker. What I did see is like an alt text for the sticker, and this is what I will be displaying now because it was pretty amusing actually, the last one at least. So let's see. Don't forget to use IPython today. Stack Underflow, thank you for the reminder. I might remember to run it. The only reason, as I always say as I always answer the question about it, that I don't use it is because I forgot to run IPython instead of Python. So there you have it. Okay, and now I guess we can get going with the actual challenges. If you have any questions, again, you have to write to Foxtrot Charlie. Like, you have to use this guy's nickname, @FoxtrotCharlie, and then the question, otherwise I might not get it in our question panel, since I'm looking more at the question panel than at the chats, actually. Cool, so, what do we have? Oh, we have unsolved 23, and this turned out to be a lie last time. Last time we solved, we were at 19, I solved like, I don't know, 4 challenges, 5 challenges, whatever, and we got more unsolved after the finishing the live stream than before, so that's pretty expected on picoCTF actually, so I wasn't that surprised. That being said, we have 53 challenges solved, and yeah, let's try to add to that some more, and I will only show unsolved challenges this time. Perfect, so okay. New overflow, yeah, let's go with this. Let's go with binary exploitation. Last time in the comments, if you look in the comments of my previous live stream, there was a person who basically pinpointed what were my mistakes in solving the new overflow last time, because it turned out I was looking at the disassembly of the wrong function when I was calculating the stack, and that's why the length didn't match for me. Yeah, because I was looking at the flag function instead of a function which I actually like, where I'm overflowing the buffer. So yeah, and then we did have the issues with push was basically crashing, or like print was crashing, or whatever was crashing the program, and I was like I don't know what's going on, but I still managed to work around it by using standard CTF techniques, like if you cannot jump to the beginning of a function, maybe jump in the middle of a function. So that's what I did, but it turned out that Canonical actually did some changes in Ubuntu, and the kernel for some versions was compiled with some flags, and if the stack was misaligned, it would throw an exception. So that's what we have fallen into. I don't think that was supposed to be there for that challenge, but whatever, like it didn't take us too long to work around that. And again, that's a pretty standard thing on CTFs, that you run into like a different configuration on the server side than on the client side. So if you can, and if you have enough knowledge to work directly on the remote server, do that from the beginning, you will have less surprises. It is way harder to do that on the other hand, especially if you do not have the context in your head yet. So, okay, new overflow 2. Okay, now let's try manipulating arguments. We have a program, you can find it here. And we have also the source code, so let me download the program, and I need to create a new directory for it. So it will be new overflow 2. Okay, and this is the source code. I guess we can zoom it a little bit, or like actually make the font a little harder. Oh, I think we already did something similar. You know what, I'm going to turn on the word wrapping. Perfect. So we have a function like this, which, yeah, there are basically 2 flags, 2 global flags, win1 and win2. We have to set them to true. Like, yeah, basically, we have to somehow set both of them to true. And to do that, we have to manipulate arguments. And these are the arguments. And then we look at this function. There's also a flag function. The flag function is being called when? Where is the flag function called actually? The flag function is called nowhere here, no. No, seriously, where is this flag function called? Is it not called? Do we have to call it ourselves, or am I just blind? Okay, it seems not to be called, so I guess we will have to call. That's pretty weird, actually. I expected that if we have to manipulate the arguments. Okay, where are these arguments checked? It's checked when 2 is set to true, and then... Okay, so no, this function is like totally irrelevant, I think. We have to actually call this is weird. Like, this probably shouldn't be here at all. Yeah, it's unintentional. So on a CTF, if you find it like such an unintentional bug, just go for it. I mean, it doesn't matter. Everyone will go for the unintentional easy bug to exploit. Go for it. No sense wasting time. We will, however, go for this one, I guess. And where is this called? This is nowhere called either. So, oh yeah, well, whatever. Let's see the disassembly of the program itself, and let's actually see what kind of application is it. Is the 64-bit binary? I do expect it to be a 64-bit binary because that's what we dealt with last time, and as expected, it is a 64-bit binary. We can also do checksec on it. Checksec. There's a checksec.sh actually tool, which I'm going to use. I think it's file vuln. Let's make the screen slightly bigger. Here we go. And it says there is no CanaRy, NX is enabled, so we cannot just jump into our shellcode, which is somewhere in memory. We do have to probably use return-oriented programming or something like that. And there is no ASLR, so the addresses which we see in the binary are the addresses which are used in memory. This, by the way, is related only to the binary, is not related to like heap, to like the stack. These things still can be randomized. Perfect, so now we can launch the, see the application in some disassembler. I'm going to use IDA. I probably could use some other thing, but like I don't have shortcuts for most of them. Okay, so here is IDA. Why am I opening IDA? First, I want to double check if the flag is there. Like the flag, yeah, it is there. Is the name of the file actually the same? The name of the file is here. Yeah, so we could just straight jump into this flag probably and game over. By the way, the buffer overflow looks like identically like the last time, meaning there is the like a buffer and we gets to it. So same scenarios in all the previous, as in all the previous overflow challenges we had. So yeah, just like a buffer overflow and do something. If we would return to this, I guess that's game over already, but let's not do it because again, these are educational streams. So let's actually jump to this function instead. And to jump to this function, it actually, well, we can see the source code. We have the source code. It does check this condition, this condition here, right? Now, how do we go about it? So to go about it, what they said in the description is like, yeah, let's play with arguments, set the arguments, and as you can see, there are arguments here which we have to set to specific values, and the same here. But this challenge on a CTF, if you would get this challenge on a CTF, this challenge isn't about setting the arguments, the challenge is again about getting the flag. So what I see here when I look at it, I see this followed by a return, and I see this followed by a return. So I wonder, this might not be possible, but I wonder if it would be possible to just like jump here, do a return chain to jump first here, then jump with the CPU here, and we have a flag set, ignore the arguments, ignore the middle of a function, whatever, we don't care. And then we just like jump here and that's it. Let's see if we can make that happen, totally ignoring the arguments. Even if this is an educational stream, I'm pretty sure we will get to more complicated return-oriented programming challenges later on anyway, so it wouldn't hurt if we just show this trick instead. So let's look at the assembly code, because the assembly is the source of all the truth. Like, not the source code, right? But the assembly actually, like, some pieces of the source code might not even appear in the assembly, or it might change really drastically. There are some recordings of my talk, I believe, from I don't remember which conference actually, from Lisbon, from Portugal, from last year, no, from this year, from February, where I kinda showed the stack. I think that was that talk, maybe that was another talk, no, maybe that was another talk, never mind. Anyway, and yeah, my point there was that don't always trust the source code, look in the assembly, and the point after that was that like assembly also lies because we have like speculative execution and friends. What I want to do is I want to jump here and let's see what's there afterwards. It's basically a NOP, it's a pop, and it's a return, which means if we would put on the stack something like this, we put on the stack the address of this move, so address of the move, right, instruction. Then we see the pop, like the pop is here, right, this pop. So we put on the stack whatever, like 41, 41, 41, doesn't matter, we don't care about RBP at this point. And then there's return address, so we put the return address of like the next thing which we want to chain to. And when the CPU starts to execute it, it will, like, we buffer overflow, here, and then the CPU goes here, executes, well, returns to this address, meaning it jumps here, it sets the global variable to 1, then it executes the no-op, which doesn't matter for us, then it gets the pops this address from the stack, and then return pops this address from the stack, which jumps to yet another function which we'll chain in. And the other function which we'll chain in is this function, which has like the exactly same thing here. So we'll just jump here with the CPU, set the flag, and then put some bogus values on the stack, it doesn't matter, do a return, and after that we will jump into this function, to the beginning of this function, and then yeah, we get the flag. That's the idea. We should see if this actually works. So I'm going to open a notepad to actually get working on this. And we have, what size of a buffer we have? We have this val, right? Let's check actually this function was the 40, it allocates 40. What's the size of our, yeah, 40. That's 40 hexadecimal. 64 decimal is 40 hexadecimal. So we have to put like 64 of A's. No, that's too much. Yeah, this is 64. How do I know it's 64? Because I'm cheating, obviously. This is 63, so that means I actually have one too little. Now it's 64 characters selected. After that, there is this push RBP, so we have to put some bogus stuff there. So let's just put 8 B's. 8 because we are in a 64-bit environment. And after that, we start putting, let's make an enter here. We start putting the addresses, right? So we put the address of this move. This move is at the address 400777. That's a nice address. 400. I will convert it to like some proper addresses in a second. Then there's this bogus thing which we do not care about. Let's put just C's there. Bogus thing meaning like the popping the RBP. Then we go here to this function and we jump to this other move. And we jump here, which means it's 7B4. 40007B4. And then again bogus values. And then we jump into this winFN. So we jump into the beginning of it. If it works, I'm going to just copy the address. And then obviously it will like go to the end and return, but we don't care at this point. It just crashes, but if it sends us the flag, we don't care that it crashes. So now this is actually a 64-bit address. So we have to align this to 16 hexadecimal digits. Perfect, then we have to do the same here, and now we have to actually convert it to little endian, so I'm going to do it just here. That's 77, you know, bytes from the end. 07, 40, and now just zeros, so we can just do 0, 0, 1, 2, 3, 4. Okay, this is fine, and I'm going to just copy it. Yeah, we don't need this anymore. Let me just double check. 77, 07, 40, 0, and 5 zeros. Yeah, that looks fine. So you don't need this anymore. I'm going to copy paste it here and just change the B4 here. This is the only thing which changed this B4. So that's fine. And here we change the 7BE. How nice that is actually so close to each other. And I can remove this. And now let's put it together. Yeah, it's fine. Okay, and I'm going to just echo dash E to, you know, escape it. And I'm going to do this, and then we are going to launch the vulnerable application. So but first we have to actually connect to a shell. Well, I am actually connected already to the shell. Here we are. But we have to go to the proper directory. So to go to the proper directory, we find my browser. Here is my browser. Here is the actual path to the problem. So I'm copy pasting it. Here we go, and here's the flag. We cannot read the flag, cat flag doesn't work. Usual setup, we actually have to exploit this to be able to read the flag. So let's see if this works, if my idea works. And no, it doesn't, because I've made some obvious mistake, but we can figure out what's happening. It might be that the stack is misaligned again. So one of the things which got recommended to me last time is just jump to some returns. So I'm going to, because jumping with return-oriented programming to a return is it's an equivalent of a no-op, of a no operation. So I'm going to do just that. I'm going to jump to some no-ops. Let me do the same which I did before. That would be for C08. And by the way, I'm doing this to align the stack. This is the only reason I'm doing it. Okay, 1, 2, 3, 4, 5. Okay. I want to preserve the original. And let me put it here, and let's see if this works. So I'm just jumping to a return which gets the next address from the stack and continues the chain. And we get the flag. So that's it. Yeah. We didn't have to match the arguments because we actually abused the fact that we can jump directly into setting the global variables which are in memory. And again, if you're on a CTF, go for the easiest way to solve the flag. Here it would be just calling the flag function. We didn't want to do that for educational purposes, but it's always a fun thing to show another bypass of, you know, you're not exploiting the intention of the authors. You're exploiting the actual code which is there. And remember, that's fair on a CTF basically. And like also in real security, obviously. So we have this, the flag. Let's just copy it. We can close IDA. Here we go. This was this task. And it's solved now, so I can finish it. What do I mean by align the stack? Okay, so this is what I was referring to at the beginning. For some reason, it seems that this whole thing is compiled with, or rather the server is running with certain flags which require the stack to be aligned to 16 bytes. And due to the way I structured the returns, I was aligned to 8 bytes. That means I was misaligned by 8 bytes to the boundary of 16 bytes. And I had to do one more return to align myself to 16 bytes. That's basically it, to maybe explain it slightly better. If we have like the stack, right? Let's assume this is the stack. Let's assume that on 64-bit you put always 8 bytes on the stack, so this is 8 bytes. But there are instructions in x86 which require 16-byte alignment. These are the instructions related to so-called SIMD, single instruction multiple data, or extensions like SSE or AVX or like MMX. No space for MMX, too bad. And there are usually two versions of an instruction, one which operates on unaligned addresses, which is slower due to reasons that sometimes you need to fetch 2 cache lines, blah, blah, blah. Actually, the instruction gets more complicated due to that. But if you have an aligned access to the 16-byte boundary, so it would be like every second address here, right? The access is actually faster because it's guaranteed that you will hit only one cache line. Therefore, you do not need any like circuitry to get to like handle the edge cases where you do some query between 2 cache lines. One cache line is, by the way, 64 bytes. So if you align something to 16 bytes, well, and by the way, these instructions read at least 16 bytes. That's not fully true, but let's assume that's true. So yeah, so if you're aligned to 16 bytes and you read 16 bytes, then you will never read from more than one cache line. And due to that, there are some flags in the kernel, and there are some, not in the kernel, like the flags in the, in the CPU that force some alignment. And also if the kernel or the libc were compiled using instructions which are operating on aligned memory, that means they expect the memory to be aligned. And when something operates on the stack and the stack would be misaligned, then the instruction throws an exception because it expects it to be aligned. It doesn't have the circuitry inside to do the unaligned reads from two places, two cache lines to merge it then. Therefore, it just crashes. And that's the problem we had, that our, like at the end, when we jumped to the last function, our stack was, for example, here. Like, which means we were misaligned. We were at like the plus, the boundary plus 8. And that's misaligned, which means I had to do another return, because another return would just eat up another 8 bytes, and we would suddenly be at the boundary, we would be aligned again, and everything would work. So this is, by the way, also something that was recommended to me like after last stream to, because what I did at the last stream is I didn't do a return, which would eat up another byte. I just skipped over one push, because a push would align the stack originally, but because my stack was unaligned and like misaligned, then skipping the push would actually, sorry, it's the other way around. I was aligned, but the push misaligned the stack. That was my problem. Therefore, if I skipped the push, it stopped misaligning my stack. Yeah. That's basically it. Like, read the details about how x86 works, basically, if you want to really get a hang of it. But yeah, we solved another challenge. Therefore, I'm going to take a look if there are any questions to this challenge. If there are some questions, so let's take a look at the questions. The questions will appear here. Again, if you have any questions, you have to actually ask Foxtrot Charlie to pass me the question. What's the topics, ideas for future streams? I will continue doing picoCTF until I solve all the challenges, and I have absolutely no idea what will be next. No idea, seriously. That's a good question, though. Is discrete math that we learn in university important, or is it just a waste of time? If you're into cryptography, that's important, I would say. If you're not into cryptography, then it's okay to learn. It won't hurt you. It will like expand your, perspective, and it will give you some flexibility in using math. That's something you do not have after leaving high school usually, unless you really like mathematics when you gain it really early on. But normally you need to do a lot of math to get a lot of flexibility with it, and that's pretty useful later on, especially in security, I would say. So some of the things on discrete math will be directly applicable to cryptography, and some of the things won't be, because it's life. But yeah, that's about it, I would say. Well, actually, I don't know what's the exactly like curriculum of your discrete math. I had, for example, stuff which could be directly applied to, I had like logic there. Okay, I think it reconnected. Do let me know on the chat when I'm actually back. It seems my internet died for a couple of seconds, well, more like a minute or so. But yeah, let me know when it works and we can continue. I think it works because I can see myself on the preview again. So yeah, what's the delay today? I don't know what's the delay actually. Back, perfect. Let's get going there. Welcome back. So, I think I did answer the first question before I disconnected, so let's go with the next question. Okay, so yeah, basically to sum up the previous question. Oh, do I have to restart this? Okay, I have to restart this. My questions do not show. I need to restart the script. This will look really funny for a second. I apologize for that. Okay. Now it's better. Okay, perfect. Yeah, so to sum up, discrete math for cryptography, for some programming, it's useful. For other stuff, not really, unless you like do something really related with it. CTF Rookie asks, do you have experience with Intel Pin or DynamoRio? Would you recommend any of them? I do not have any personal experience with either of them. Well, okay, maybe I did the tutorial. That being said, I do know of both of them. I do know how both of them work. And I did write my own similar engines to Intel Pin in the past. Not as good, in all honesty, but I did write them. So would I recommend any of them? Both. They work differently. They do different stuff. So if you know both of them, that's actually useful. Because like Intel Pin might be better in some cases and DynamoRio might be better in different cases. Do try to understand how they work internally, because that's actually pretty fascinating, especially in case of DynamoRio. Implementing Lisp interpreter in LLVM. No, Lisp sounds like functional programming. That's not really my thing, sorry. Following on the discrete math question, how important are data structures and algorithms in InfoSec? That's a nice question. I guess the answer here is they are both. So it's like this. At places, they're super important, but not often. Like, you might sometimes run in a situation where knowing an algorithm is crucial to security. That doesn't happen too often, but it sometimes happens. And sometimes, again, not too often, when creating a tool, you need like really good knowledge of some algorithm. So I did some courses on algorithms. I did play some competitions, but I'm not an algorithm guy. So what I do in such situations, if I like really need strong algorithmic skills, I just look for Redford or Euro, because they're way better in algorithms than I am. So yeah, I use their knowledge and then I continue with whatever I was doing. But again, doesn't happen super often, like let's say once a year. Sorry, more like maybe once per 2 years. Yeah, that's basically the answer here. On the other hand, you need to know the basics in programming, and you do need programming to do like more create InfoSec tools, basically. So learn the basics. If you're basically on a uni, learn whatever they have to offer about algorithms on the uni, and that will be a good thing. You don't have to go above that. You do not have to go for competitions for like top coder or whatever, right? But do learn what they offer on the uni. That's like basically the minimum, I would say, but you should know, you should understand about algorithms. By the way, like a random like tip or trick, whatever. If you're learning algorithms, right? I think, and this is like what did not work for me, reading from like a book like Art of Programming or like Introduction to Algorithms or whatever, reading the text from that and trying to work with the algorithm based on that doesn't really work at the beginning, especially maybe later, like it's an acquired taste or something. What you should actually do is the reverse. Start with finding an animated version of the algorithm where somebody explains it and there's an animation of how the algorithm works. That usually gets like a click. You start understanding what the algorithm is supposed to do. Why is it implemented in such a way? And after knowing that, read the definition from the books I mentioned, or like from Wikipedia or from whatever, right? But really, an animated version of an algorithm, like a video or an interactive website which actually shows you how the algorithm like moves the nodes around, that works like wonders. Okay, I think my internet died again, so yeah, it's not easy today. But it's still, I think, or is it? Did it? Yeah, it seems still there. Okay, really? Because I do not have internet, it seems, so how can you see me? If you can still see me, that means there's something really interesting going on with routing. Okay, so I'm not going to answer the next question because I have no idea what the next question is because I got disconnected from the question panel. Which means we can go to the next challenge in case it actually loads for me. So this is going to be an interesting stream. That's fine. Okay, here we go. What does ASM2 and something like this return? Okay. Okay, no idea what that is. Submit the flag as hexadecimal value starting with, oh, I know, this is like a same kind of challenge we did solve before, meaning there is some implementation probably here of this function and we have to figure out what this returns. The last time we did it by cheating, basically, which means we actually ran the code and saw the result and that was it. But let's see if I can load it. Yeah, I could load it, so we can solve it still without actually having too much of an internet access. I see that even Discord died on me, but YouTube chat, I can still see it, and I can still see... I think I can still see IRC, which is good. Cool, so the source code looks the following. We are basically... Okay, so last time I did solve it by basically running the code. This time I'm going to solve it by actually analyzing the code. So let's see what's going on here. This is like a standard prologue to a function. Like this is, I would say this is part of it. You might disagree. This is just allocating on the stack, like allocating. It's just like a logical allocation. It's allocating 16 bytes on the stack. Then we are doing what? We are reading from EBP plus, this is reading an argument. So if we have a stack, right? We have a stack, this is the stack. And we have like the return address here, this is the return address. Then after the return address here, we have the arguments. So this is like, the arguments start from return address plus 8, but I'm not going to mark it here. And then on this side we have the EBP. EBP is going to be pushed here. Then we have 16 bytes. And by the way, we push the EBP and then we put the ESP in EBP, meaning that EBP is pointing here to this place. Meaning that if we have, and this is by the way 32-bit assembly, so remember that each thing on the stack has only 4 bytes. Which means that EBP plus OXC was three stack elements. C is 12, each element has 4 bytes, so 12 by 4 is 3. So this is like plus 0, plus 4, plus 8, and plus C, meaning this is the second argument. So we have the second argument here. The second argument is being put in EAX. We should actually start noting this. So here is like the second argument, EAX equals, I guess I can show you how, when you're learning reverse engineering, I can show you how you could do it. And in this case, you could do it like this. A really good exercise is to basically translate the code which you see into C code. Or like, if you know any other language, like for example, Python, it can be Python. Let's do it for Python, because why not? So this is basically my, let's assume this is Python. I'm actually going to copy the file and rename it to py. By the way, re-implementing some algorithm in Python while reverse engineering is pretty standard, especially on CTF. So, okay, let's do, I think there was a, yeah, I just commented out. And I do create a function which is called asm2. I do know that there are 2 arguments because, well, that was in the challenge description. So there is arg1 and arg2, or like arg0, arg1, whatever you like. Perfect. We ignore this. We do not translate this. This is just a prologue. We do translate this. We put in EAX this is, as we did already say, this is argument 2. So we put in EAX argument 2. Here, EBP minus 4. So I'm going to actually draw the stack again. And Yeah, let's just do it like this. Let's do this is, let's assume this is 4 bytes. So 4 bytes. Okay. And let's assume that the return address is somewhere here. So this is the return address. Here is the argument 1, argument 2. And therefore here is the old EBP. Old EBP. And this is where the EBP is pointing to. So let's do it like this. This is where EBP is pointing to. And which means these will be basically local variables. So let's call them from this side A, B, C, and D. I apologize for the misaligned A. How do I know that there are 8 of them? Because, oh, sorry, 8 of them, 4 of them. I don't. It might be like 16 1-byte variables, but we'll figure it out in a second. For now, just like temporarily, I did assume these are 4 integers on the stack. It might not even be 4, it doesn't matter, we don't care. Let's continue. Here, EBP, as I said, basically points here. That means EBP minus 4 points to D. So in this case, D is equal to arg2. Then we translate this one. This is EBP plus 8, and we put it in EAX again, so that's arg1. We know that if this was plus C, this is plus 8. C, 8, 4, 0, and then minus 4, and so on. Here, we basically get minus 8, which means this is here, C, so C is equal to EAX. We could simplify it already, we could just say like ignore EAX, we know that these 2 lines basically do this, and ignore EAX, we know that these 2 lines do arg1, and that's fine. We can simplify it now, we can simplify it later, usually do a couple of rounds of simplification. Then we jump to 5C, which is ASM plus 31, which is here, so we jump here. And we compare if EBP minus 8, so here, yeah, we jump here. We usually want to take like a compare and a jump as one instruction, because that's just one if, or actually one condition in an if, because it's quite funny if you write like if A and B and C, this is actually would be translated to 3 different compare and jumps. So 3 different ifs, basically, 3 different blocks. But here, yeah, we have one. And it compares, so it's some kind of if. I will figure out what kind of if it is in a second. We can translate this. This is less or equal. Jump if less or equal. And this is by the way Python still. So we compare if minus 8 we know it's C. So if C is less than or equal to this value, I might get the jump wrong. That's fine, we will get to it. Now, important thing here is that this is a signed jump. There are like 2 types of conditions. There's unsigned and signed condition. Depending on this, you actually know if the variable is a signed integer or is it an unsigned integer. So yeah, I hope this doesn't matter too much, but yeah, we know it's an integer right now. Pretty sure it's a 32-bit integer. So that's fine. If so, then go to and whatever. Oh, there is no go to in Python. That's fine, we will get to it. After we translate everything, we will get to a phase where we actually do proper code from it. And then if we do not do the jump, we get here and an EAX. EAX is the return value. So this is the return value, setting the return value. This is due to the calling convention. We do a leave, which is basically a epilogue and a return. So this means return, and that's minus 4, EBP minus 4. So we did establish that we call this a variable D, which means we do have to go and jump here. This is a jump, so we have to continue with these 2. What's going on here? Here we take the D and we add 1 to D. So yeah, is it D? Yeah, it is D. And we add 1. That's fine. Here we go to C and we add OX A9 to C, and then we jump here. So we know this is basically a loop. This is a for loop or whatever. In C we would say this is a for loop. In Python we are going to say this is a while loop. So basically we need to translate now this part into a while loop. I am going to leave this code here just in case I make a mistranslation and I have to look it up. So yeah, I don't want to remove it yet. But in this case, I basically need to do while, and I can check this condition at the beginning. It doesn't matter too much. So let me check it at the beginning. While this, do this. And this is, by the way, there's a mistake here, but I think I'm going to let it pass. The mistake here is that Python operates on very long integers, on big nums, like big numbers, meaning it doesn't really have a limit of how many bits there can be like used to express a given number. It will allocate more bits if they are needed. There are no overflows. That is not true for x86. Oh, by the way, this is basically a multiplication, right? But yeah, anyway. So yeah, so basically, if I would really want to correctly emulate it, instead of writing d plus something 1, I would write like this. And then grab it, truncate it to 32 bits. So I'm going to do a mask, a 32-bit mask, and an AND operation of a number is basically truncation. And I do the same here. It doesn't matter here because I don't think we are going to overflow it, but it usually does matter. What's more important is that this gives you an unsigned number, and here I did mention we have a signed jump. But I'm just going to ignore it because I'm pretty sure this will work anyway. And again, this is just a multiplication because like adding something in a loop, this amount of time, well, this isn't really this amount of time, this is like a subtraction of the arguments, whatever, it doesn't matter. But yeah, this is basically just a multiplication. So yeah, that's it. Now we have to print the ASM2 of the arguments which were specified here. So I'm going to just copy these arguments and I'm going to run it. Let's see what's going to happen. I'm going to run it on a Linux console, I guess, but doesn't matter. Okay, we get this result. Do I trust this result? I do not trust this result. But why do I even bother adding something to C? Because we are comparing C here. Okay, no, maybe it's fine. Maybe it's fine. So maybe this isn't a multiplication at all. Maybe it's just a division or whatever. Yeah, anyway, do they ask us to... Yeah, we have to give the answer in hexadecimal. So I'm going to put hex here and we get this number. And it might not work depending on if I get the conditions correctly. I might be off by 1, that's pretty normal, but this time it actually did work. So yeah, this is a pretty standard approach to some reverse engineering challenges. You do not do this translation to everything, but there are pieces which you want to translate to a higher level language so you can instrument it easier. You don't do it always, but you do it sometimes. And like the harder the task is more probable that you're going to transcribe something to a higher level language. Also, this kind of an exercise, I really recommend it if you're just beginning with reverse engineering. Do a lot of these translations because they will help you understand the code better instead of just like looking at the code and like having everything mixed up. Translate it to a higher level language that you know. Cool, so that's that, and we did solve another challenge. Perfect, and we got another unsolved challenge, yes. Now we have a binary exploitation, CanaRy. This time we added a... Oh, by the way, I'm going to take a look if there are any questions. Okay, any advice for new cryptocurrency traders? No, no advices on like any trading whatsoever. Topic idea version 2, implementing own language in LLVM. We might someday. We actually might someday. That being said, there is actually... That's not an easy topic. Like, I did start going through some tutorials because I need to implement a backend or a frontend for some of my projects, and yeah, there's like a lot of stuff you have to go through. So maybe. Okay, cool. So we can go back to this challenge. CanaRy, yeah, this time we added a CanaRy to detect buffer overflows. A CanaRy is just basically a value which is on the stack between local variables and return address. And if it's like a random value basically for all intents and purposes. You do not know it as an attacker. So like, okay, like if you overwrite it, it will get detected that you have overwritten it because the value changed and is no longer the value it should be. Therefore, like the program just like is killed instantly. Like it doesn't even get to executing your exploit, right? It just killed. And it's a pretty old actually mitigation, and there are like countless bypasses to it. There are many implementations of it. Like if you look at the paper we released with Yuru, I think in 2010-ish, we basically showed how to bypass, how to like guess the value of the CanaRy for Windows kernel that was still Windows XP kernel, but yeah. So okay, welcome back, I think. Yes, it happened again. But this time it was actually my fault, since you know, I have internet, like there's a modem and you have to put coins in, and I forgot to put enough coins in the modem, so that internet basically ran out of money. Yeah, but we can get going with it, and we do not have to play the Dino game anymore. So let's just download it again. I'm not sure really what you heard last time, because I did notice it pretty late that the internet connection died. I see, but I still do not see it on the preview. Oh well. Let me refresh the dashboard. Okay, anyway, we are now solving the CanaRy problem. Basically there are canaries, and yeah, we can continue with it. I think I'm going to do one more thing this time around. Yeah, usually the internet is like works really great, but you know, from time to time something has to break. That's how technology works. Cool. The name of the challenge is CanaRy. And I'm wondering if I downloaded. Okay, I downloaded, I think, the correct thing. Perfect. So let's take a look here. Oh, before we go over, I'm going to actually check if, like, what's the bitness of this. So, can 64-bit CanaRy be bypassed? Yes, but it really, so bypassing mitigations, like you can, if you have just a buffer overflow, and like you usually cannot do too much about it, but it starts like to go into the details of how the CanaRy is implemented. Is it a server or fork server? Is it a what do you have on the stack, and so on? And they're like, and maybe you have another bug which you couldn't read the CanaRy from the stack. So there are like many different things which you can use to somehow bypass the CanaRy. And you do not attack it directly. You sometimes do, but you rarely attack it directly, and you usually bypass it somehow. So let's see what method we will use here. There are several methods which are like really well known. And okay, so this is going to be weird. I already see that is going to be weird. So file vuln, I probably should rename it. It's again 32-bit. So we are back in the 32-bit land, which makes it slightly easier probably. Checksec -file, and let's go with vuln. And okay, I'm going to rename it. Okay, no CanaRy found. So this is not a standard CanaRy implementation. This is an implementation, a custom implementation implemented by the challenge authors. NX enabled, ASLR enabled. Why is ASLR enabled? Well, whatever. And there is quite a lot of code. Okay, so let's get the analysis on the roll. We have like courtesy code again, which helps us, like makes the challenge a little bit easier for us. Then we read the CanaRy and we go to vuln. Let's look in the vuln function. It's pretty long actually, so let's look in the CanaRy, sorry, read CanaRy was it called? Yeah, it is called read CanaRy. So yeah, we open this file, which is like some CanaRy txt file, and it says like, yeah, whatever, like if it fails, it just exits. This isn't a hard exit, by the way, it's still calls destructors that are registered. I do not mean like class destructors, I mean you can register a function as a destructor, and then it's called at the, well, basically at the end of a program. So this isn't like, usually you just exit immediately, but like usually when you find that the CanaRy is incorrect, this isn't obviously a CanaRy incorrect problem, but good that they have an exit here. I digressed. Then we read klen of, yeah, usually you just write one here, so I get confused for a second, like either reading just one byte of a CanaRy, what kind of a CanaRy is that? But no, I misread the code is actually reading klen bytes, and it puts it in the key, which is a global variable of type char or char, however you want to say it, and the key length is 4. So 4 is fine, but it's actually, yeah, so one important thing about this CanaRy implementation is that it's constant. It's a constant CanaRy. If we have access to this file and we can read it, it will be always the same CanaRy. That's a little funny, and that allows a certain class of attacks. That doesn't usually happen like this. Okay, I'm going to tell you a secret. In Windows XP, the kernel itself, not the drivers, but the kernel itself had a constant CanaRy, but you could just read from the code. Yeah, but from that time, it usually doesn't happen. You have constant CanaRy in one case, when you have a fork server, where you have like basically a binary which forks itself and then like handles the client data, and when another client connects, it forks itself again. In that case, all the children processes have a constant CanaRy. And there is a certain very interesting type of attack for it, where you can brute force it byte by byte. So this is probably going that direction, and we'll probably do it. Cool, so let's look at the vulnerable function in that case. We have, yeah, as you can see, they try to put the CanaRy here on top of, like basically when you have the return address here on the stack, then the CanaRy would be put here, and then the buffer would be put here, and then the user length would be put here. So it's basically like in the order of declaration, it goes like right to left. It actually went like that in the past. Currently, there are some mechanisms which reorder it to make the CanaRy most effective. It tries to put the buffers next to the CanaRy, basically. But the rule of thumb is that, yeah, it goes right to left. So the return value is here, then the CanaRy, then the buffer, and then the user length, whatever that is. That is also buffer size. What is our buffer size? It's 32 this time around. Let's change the color. Perfect. Now we have count uninitialized x0. We copy the key to the CanaRy. This is usually how the CanaRy works. You have a master key, a master cookie somewhere in a hidden location, nobody knows where, and you have a CanaRy, and you basically override the CanaRy. So the CanaRy on the stack with the master cookie at the beginning of the function. Then it asks us for some interaction. Please enter the length of the entry, and if it checks if x is less than buffer size, then it reads from standard input into this plus x. It reads, so basically that's a loop. It reads 1 byte. That's a pretty decent, usually pretty decent implementation. We'll figure out if it's really decent in a second. And yeah, it reads it here, and then it sets oh, sorry, if it finds a new line at the end. So as you can see, it ignores, like, again, it ignores binary zeros. It just cares about this character. This is the terminator. And then it increases x. So, and x is, okay. Please enter the length of the entry. That's pretty weird. But I guess it expects us to, yeah. That's actually pretty decent. It reads the text value and it puts it into the buffer, and then from that buffer, there's one problem here. We'll get to that in a second. And then it basically tries to read the value, like from here. Sorry, it tries to convert the string to an integer. That's what I wanted to say. Now, the problem here is that it doesn't add the 0, and there are no guarantees that there might be a 0 on the stack. There will be on the stack 0 here, probably, not necessarily. So this might be a little weird on the scanf. The scanf might actually, if we put like zeros only, then it might actually, like go to the next buffer and try to read some bytes from that. We might not be able to actually abuse it in any way. Okay, and then it reads the input, and it absolutely trusts the input, the size we give it, which is perfect. That's the buffer overflow. Like, there are no checks here, there should be checks here. Okay, and then if it compares the CanaRy, and if memCompare does not return 0, then it, again, like it does the destructor calling. It shouldn't do this. There is a function _exit, which does like an immediate like exit, or you can just call the syscall to exit. But yeah, this actually goes to the destructor. I'm kind of tempted to just override the CanaRy and see if we have a vector to override some destructor. But whatever, let's not go over maybe. It would be pretty hard to do that anyway. Yeah, so if the CanaRy mismatches, then it says stack smashing detected, corrupt CanaRy value. There is another attack of leaking a CanaRy that we could use here, but we couldn't, because usually after this this thing, it does display the name of the binary, of your binary, which is taken from the stack. So if you overwrite enough of the stack, you can overwrite the pointer from where the name is taken, and you can point it to a cookie which you want to leak, and you just leak it. So yeah, that's a little bit more complicated than I just said, but there is a way to do it. Anyway, okay, so now where's the flag, and basically it... I wonder why it does like the flash if it already removed the buffering. Oh, it removed the buffering from... No, it removed the buffering from this. Why does it do a flash? This is not needed here, this is redundant. Anyway, and it jumps to... Well, it doesn't jump, we have to jump to this display flag function, and it just... Again, this is redundant, we don't need it. Yeah, so we know what we need to do. We basically have to somehow cheat the CanaRy. We know the CanaRy is constant, we know the CanaRy is 4 bytes, and we know that in the end we want to jump to the flag. And that's basically it. Yeah, I don't think there will be anything fun on the stack that we could abuse here. So, yeah. That basically means we need to figure out how to attack the CanaRy. And the way you attack the CanaRy here is identical to how you attack a CanaRy on a fork server, which as I mentioned before, you basically have also a constant CanaRy for all intents and purposes there. So you do it like this. You basically, let's assume that we have a buffer, and the CanaRy, like buffer, we have a stack, right? And the CanaRy is here, this is the CanaRy value. And so let's assume this is like the 1 byte, this is the 2nd byte, the 3rd byte, and the 4th byte. And then there is like some garbage here, and then there is the return address which you really want to overwrite here, right? To jump to your shellcode, or to like your return chain, or to the display flag function for the flag. CDF rookie writes that the thing I mentioned before was fixed in new libc. Yeah, it was. That's great. There are still some aberrations, but whatever. Anyway, so and this is the buffer which we basically have, and which we can overflow the cookie. So yeah, what you want to do is you do not want to overflow everything and just write the return address. What you want to do is you start by overflowing just 1 byte. Because 1 byte, like the whole cookie, is 4 bytes. How many possible combinations there are? 4 billion. That's a large number. We could brute force it locally. Yeah, we could. But if it would get to like, 64-bit, we could not brute force that. So, and this method, by the way, also works for 64-bit. So what we do here instead is we try to overwrite only 1 byte, and then because 1 byte has only 256 possibilities, so 256, right? So you start with a byte 00, and then you go to byte up to byte FF, like calling the exploit each time anew, each time again, restarting the exploit with the next value. And on most of the values you will see stack smashing detected, exit. That's fine. On one of the value, the correct value, you will not see that error. It will just like normally exit. And that's what you are looking for, because when it normally exits, you know you hit the correct value of the canary. So now you know 1 byte of the secret canary. What do? You go to the next byte. You go to this one, because you already know this one. And you start brute forcing the same way this one, only 256 combination. And at some point it will not say stack smashing detected, and then you get the second byte. You do the same with the third byte and with the fourth byte, and then you have the whole cookie with only 1024 tries, iterations. So this is basically how you have to get the cookie. And after doing that, well, you know the cookie. You can write the correct value of the cookie there, and then happily override whatever is else on the stack. So this is basically what we want to do, and we want to go for that return address. We want to jump to the display flag, and that's basically it. What do I mean about exit destructors? How can I define one? Let's digress here for a second, because I already mentioned that. So basically, let's assume we have like int main. Let's do okay. And let's put here ASDF, and let's return here 0, whatever. Now you can define a function like, for example, void ASDF void, and let's say we want to print it as a destructor. Okay. And we want another function, let's call it ABC, and let's call it a constructor. Now, it depends on the compiler. On GCC there is an that's lspec, declare specification constructor. No, that's not a dev, that's an attribute. Sorry. Yeah. Exactly, like attribute and constructor, and this is what we want to add here. Like, it can be added in whatever place, almost. Attribute, 2 brackets, that's really important for some reason, I don't know. Okay, I think that's actually, no, that's fine. Okay, and here we want to do the same with destructor. And now let's compile it. GCC ASDFC. And let's run it. And basically, as you can see, the constructors are being run before main. Like, this is run before even the application enters main. And then, when the application leaves main, it starts running destructors. So this is why we have the constructor first, then main, and then the destructor. And if we do an exit here, I think exit is an stdlib, right? Okay, let's do an exit here instead. Like a normal exit this time around. And as you can see, the destructor is still being executed. So like even if we do like before ASDF, it's still being executed. But if we actually do an exit with an underscore, then it exits immediately. It says an implicit declaration, but it still links correctly. It's probably in UniSTD or something like that. And yeah, and then the destructor is not called. Yeah, so how it works is basically like C library maintains a list of functions which have to be called. If we actually look at, you know what? Let's compile it like I'm going to remove this because I'm a little worried about that code optimization. And let's take a look in IDA. Okay, and now if we go to this, no, that's, yeah, there's basically this like fini array thingy section and init array, like these two sections. If you go there, you will have the like basically addresses to, it's a table of functions which have to be called before, like table of constructor before main. This is the like ABC, right? This is the constructors. And then there is a table in this fini array, like fini of finishing table, which is a table of destructors which are going to be called after the main returns. So basically main returns like, it's like this. The application starts with libc start, with the function which actually calls this with the entry point, right? And the entry point calls this, like puts these two tables, the pointers to these tables, and the pointer to main as well. Sorry, you have a pointer to main and these two tables, and calls a function which is called libc start main. And this function basically is responsible for calling the constructors, then calling main, and then calling the destructors. It's also like setups the environment for main. It makes sure like all the pointers are in the proper places in memory, and so on and so on and so forth. But yeah, that's basically it. And it never reaches here because at the end of this function there's an actual exit syscall. Yeah, like it's quite interesting, right? Even if you have a hello world application and you start reverse engineering it and going deep and deep and deep, there's a lot of code which is being executed, and I mean a lot. So yeah, that's a digression about why I mentioned that don't use exit, use underscore exit in such cases, or abort or whatever, because that way the destructors will not be executed, because it might be that the destructor actually uses a pointer which you were able to override, and then yeah, or like you still get execution even though a stack smashing was detected. Anyway, so yeah, let's get to the implementation of a scheme I mentioned. And before we go there, what I would like to do is, do I need to refresh it? I do not need to refresh it. I want to go to this directory. Did my shell... I'm still connected. I'm still connected. Thank you, TCP/IP, for actually working correctly. So I need to go to this directory. Yeah. And I'm pretty sure we cannot access the CanaRy. Yeah. No access to CanaRy. I'm going to try it anyway, just in case. Always try it. Always try the flag too, because why not? And yeah, so we just have to basically figure out how to exploit it. And yeah, enter the length. I'm going to enter the length like 1, and now I just put 1, and yeah. Why is this scheme here with entering the length and so on? This is basically to give the user, the player, a chance to control the actual data written on the stack with byte precision. This is like, again, to make the task easier. You do not always have a situation like this, but this time we have, so let's just use it. Cool. So now where's the flag? What do? We do need to automate it. Again, as I said, it's like 1024. That's the worst case scenario, by the way. Attempts which we have to make at this. Is there Python here? There is Python here, so I'm going to write a Python script to actually do the exploit for us. Let's call it go.py. I am going to write it locally first, and I'm going to call it locally. So what we need is, I'm going to go with Python 2, right? Yeah, Python 2.7. So import subprocess. I'm pretty sure I'm going to need that one. I'm going to need 2 loops, and okay, and I think that's about it. I am going to open this application in IDA as well, because I need to check the offsets. I do not think we have to worry about stack alignment this time. We do need to figure out what's the overflow address actually. Well, more what I care about is actually like getting the, where's the cookie set? The cookie is set here. La EAX, yeah, that's the key. Then here S1. S1 is where the cookie is placed. So here I'm going to jump to this view. Yeah, so the cookie is only 4, so then there's var c after the cookie. Whatever is var c, I don't know. And then basically we have what, 12 bytes after the cookie until we get to S, and the return value, the R is the return value even after that. So 10 bytes hexadecimal, 10 bytes is the difference, the distance between there's the buffer, the cookie, 10 bytes, and then the return address, which will be useful later actually, when it's not really useful now. So, okay, so let's do a function, let's call it call, and let's give it, what are we going to give it? We are going to give it the length, like a z, and 4 numbers for the cookie, like 4 bytes, A, B, C, D. Okay, so the cookie in our case is, so no, actually the payload, which is what we are going to send to standard input. So the payload is empty, then we add to the payload the number of bytes, so that's actually going to be just like this. Remember about the enter at the end. Then we need to add basically whatever is the amount of bytes. Oh, did it disconnect again? I wonder. Do let me know in the chat if we get disconnected again, because I see that there are some issues. Okay, I think I'm going to wait for a reconnect, just in case, but we actually did really get disconnected. No, it works. Okay, that's weird. Okay, that's fine. If it works, I'm just going to continue. Perfect. So now what I need to check is actually what is the buffer size here. The buffer which we are overflowing was 32. So I need to obviously write 32 A's, so A times 32. Now what I want to know is the buffer actually the buffer which we read into. So this is this buffer. It's 30, then the buffer is size 20, which means at 10 there should be the S1, which is the cookie, which is correct. Okay, so there's the buffer, and immediately after that there's the cookie. There are no spaces, so that's enough. Like assert SZ is like actually larger than 22. And then we add the we can add all the characters B, C, and D, even though not all of them are going to be read by the application. That's fine. That's fine. It's not a problem for us as long as we know what we are doing. And this is the payload which we are going to pass to the application. So now we need to call the application and get back the output. And to do that, I'm going to use the sub process call, I don't know what. Python sub process popen probably? Oh, I cannot. Okay, perfect. So yeah, sub process. This is me not knowing Python. Popen, and then it gets the argument, which is going to be vuln, and then that's fine. That's actually it. But now we need to do the redirection. So that's sub process stdin. No, that's stdin equals subprocess pipe. And we do the same with standard output. Yeah. And then we do pcommunicate with payload. And here we do get standard output and standard error, I believe. And I hope this is going to work since I didn't do it. What if the 1 byte of the CanaRy is this byte. It doesn't really matter because we don't really actually need this either. I just added it there due to, like, if there would be buffering, usually this clears the buffer. But here we do not have to worry about it because we are actually, the data is being read here using read. Like, or actually if we use if we look in the source code, here there's a read. It's not in a loop, there is no comparison, it's just read all the bytes. So it can be a new line, it doesn't matter, it's fine. That's a really good question, by the way, because sometimes it matters, not in this case. Okay, and now I'm going to, I guess, just print standard output and see what happens. So let's do call 33 and then like the zeros. Okay, and I'm going to run it locally, obviously, first. So am I in the proper place? Yeah. Python go py. It says that popen has no attribute close. Really, it doesn't. But it does. Okay. Communicate closes it anyway. Error trying to read CanaRy. I need to create the CanaRy, like, let's go with ASDF. Dash n and CanaRy. What was it called? CanaRy 1 or just CanaRy? It's called CanaRy, just CanaRy. Okay. Okay, it says blah blah blah, error trying to read CanaRy because it probably tries to read it from a weird path, and I'm actually not at that weird path. Show me, where are you trying to read it? Let's go. Oh, I think my internet is back again. So in case I have any problems with popen, I can actually check it. No, seriously, where is it reading from? Here. Yeah. Okay, so the reading from this path. I'm obviously going to open a hex editor. I'm going to patch it out. I do make a copy first of a binary, then I'm going to look for that. So I think problem, yeah. And I'm going to change this starting here. I'm going to just write canary.txt, and then I'm going to insert a null byte here. Yeah. And let's try it again. Okay, yeah, perfect. Now it detects that there is a stack smashing in progress. I'm actually going to change this assert here to more or equal, and I'm going to change it here to 2 so that no stack smashing is actually being done. Okay, that's fine. And now what we have to basically do is we have to like just grab this. Oh, by the way, am I sure this is working? I'm sure this is working. So return this in, not in standard output. I think it's in standard output, right? And we take a look if it's in the, yeah, it's printf, so it's standard output, not standard output of errors. And yeah, that's it basically. So what we are going to do is we are going to do I'm starting to like regret this not being a, yeah, let's change it to like tab, like t here, t of 1, t of 0, t of 1, because we can do a nicer loop in that case. T of 3, okay, perfect. So now what we go for is we basically go for I in x range of 4, because we have 4 bytes, right, to brute force. And now if this, and here we go for the CanaRy. The CanaRy is CanaRy, as we know it, and we do not know it, is basically an array of zeros, because we start with zeros. So we put the CanaRy here. And if the call returns true, which means this was not detected in standard output, everything worked. That means we actually can continue, like print the number. So let's print the number like hash, maybe like this. Okay. Okay, reconnect successful, which means you should start seeing me again. So, welcome back. Yeah, it was another dead. Let me know when you see me again on YouTube. Yeah, the internet is really like behaving weird today. Okay, perfect. Hello again, so we can get going. Anyway, so I don't know when you were disconnected. I basically implemented the for loops, and this CanaRy thing here, basically it starts with just zeros, and then for each byte, it goes through all the byte values and it sets on the given index a given byte value, so starting from index 0, starting from here, and it starts to iterate it like 0, 1, 2, 3, 4, and so on up to 255. And then it calls the binary, yeah, it executes it, and it checks if stack smashing detected was in the output. If it is not in the output, then it just prints the number and it breaks, meaning that the value will be embedded in stone in on this position, because it jumps back to this loop. This loop selects the next byte, and like the process continues. And when we run it, yeah, we basically get the CanaRy really, really fast. In our case, this is done locally, so now I need to do it remotely, and I'm still connected. Okay, that's fine. So let me put in my home directory go.py, and I'm going to copy paste the code which I've written, and now I'm going to just run that code in go.py. Yeah, and it says no such what? Oh, yeah. Okay, and we got the yeah, like let's see what we got actually. 55, that's 7. Okay, 97, that's A, 7A, 6. 7A, 6H, that's our CanaRy on the server, so 7A, 6H, and now we can just work from that, we can just make a normal exploit. So yeah, let's do it. Okay, we can use the same thing here, sorry, but we just need to, I guess like just comment this out, because I already know the CanaRy, right? And, oh, perfect. If it couldn't get any better, I'm running out of disk space for the recording, but that's actually easy fix. Perfect. I removed some random files from my system directory, should be fine. Cool. So now I'm going to reuse this code, but I'm going to add another thing here, which is the actual shellcode. So let's put it like actual payload. It's empty at the beginning, and I'm going to squeeze it in here, so payload. Cool, and now I need to get the CanaRy, set it to proper values, so let me just set it to proper values. Okay, the sound is back, right? Should be fine. I see it should be back. And we do a call. By the way, there was we need to put in the payload the 10. Payload, we need to set it to, there were 10 bytes hexadecimal, as we said on the stack. And then after that, there was the return value to the address of what was the function called? Like display flag or something like that? Yeah, display flag. Where are we located? Display flag. We are located at 7. Okay. So this is where little endian comes in, because we have ASLR enabled, so this may be anywhere in the memory, right? But the good thing is that from the vulnerable function, we return, like when we go to the return, right? We return to main, and main is just here at this address. So the call to vuln is here, meaning it's and ASLR is basically only randomizing this part. It never touches the lowest 3 nibbles, lowest 3 hex digits, or like 12 bits. It doesn't touch them because ASLR randomizes, ASLR related to the binary position in memory. It only basically moves the pages, the memory pages around, but not the content inside the pages. So the content inside the page will be at the same offset. The offset in the page is 12 bytes. This is why I say that this part is not going to change. We have absolutely no idea what this part will be because, again, ASLR. That being said, it still should be fine because we can well, it's too bad it's actually A here, because if it wouldn't be A, it would be something like 7, for example. We would just overwrite the last byte of the address to the display flag function, and we would be home. That would be it. Otherwise, we have to probably brute force it again. We will have to brute force 1, like 1, 0 here, because, you know, like 2 digits makes a byte. We know that 7 is in the address of the display flag. So we know the 7 is here, but we will not know what the 0 is in the binary itself. So we'll have to brute force it. So that's just 16 values, right? So yeah, we'll have to do a brute force of 16 values. Or we actually do not have to brute force it. We just set it to a value and we run the application like 16 times or 20 times and we'll hit it. So yeah, that's basically it. What's the difference between ASLR and PIE, or PIE, or whatever we want to call it? ASLR is the name for like every idea related to randomizing the position of something in memory. PIE is like position independent executable. It means it's an executable which is compiled in a way which enables it to be randomly moved around in memory. That's basically it. So to have an ASLR enabled for a given binary, you need it to be compiled in a way that it can actually be moved in the memory. Because if it's not compiled, it expects to be on a certain address. It will like refer to global variables on a certain address, which it expects them to be. But if you put it somewhere else in memory, the global variables will not be here, right? Because it just got moved. So that's why you need to compile the executable in a special way. There are a couple of ways to go about it, but yeah, like position independent executable is one of them. Another one is like just relying on relocations. But yeah, like Windows did one in the past, and Linux did the other, or Linux did actually a combination, but that doesn't matter. So, okay, so now we are back to overwriting the return address. We are sure about this ed thingy, so I'm going to add a byte of ed. And then we, as I said, we have to brute force the next byte. So we know the 7 will be here, but we do not know what else is going to be here. So I'm just going to settle for 0, and I'm going to run it like 20 times. Because the 0 is random, it will sooner or later hit a 0 at that position, and we'll get the flag, hopefully. And this time around, I'm going to actually do a print here. Now for the size, for the call, we are 32 is the buffer size. Then we know the CanaRy size, right? That's 4. Then we know that there are like 10 garbage bytes. Like, they're not really garbage, but we do not care about them, so let's just call them garbage bytes. And then we overwrite only 2 bytes of the return address. We do not overwrite everything, we only return the 2 bytes, one which we know and the other which we know the 7 of, and we do not know this. So we have to brute force it. The rest of the address will be like the same for the display function as it is for the main function, because this is a really small binary, and like the other bytes will just, the higher bytes will not change for this number. Cool, so that's basically it. I don't think we have to do anything more here, so let's just upload it. I'm going to do this, and I'm going to do, where are we? This is not, did anyone see my shell? Here we go. Okay, so let's put it in asdf.py. Why do I have a... Wait, why do I have a this here? Because I probably pressed like a, you know, habit from Vim. Okay, and now let's run it. So asdf.py. Okay, it doesn't work. It doesn't necessarily not work either. Oh, right, because we called it only once, we need to call it 16 times. I could run it in loop in Python, but whatever. Yeah, I don't have a flag yet. Why do I not have a flag yet? Let me think. Let's look at the main again. We have this. We should actually get the flag. Oh, did I make the mistake? You're saying on chat that I made a... No, this is fine. You have defined payload 3 times in a script. No, it's fine. This is like oh, here. Okay, thank you, Savo. Yeah, like stuff. Because it doesn't really matter. Thank you. That's like a nice shadowing bug. A reverse shadow bug, basically. Which I did. Shadow is like the other way around. Let's try it again. You know what? I'm going to insert the loop here. So for I in x range 32, because this should be the how much we have to actually go for it. It doesn't complain about the CanaRy being incorrect, so I'm quite happy about that still. This, yeah, that's fine. Okay. Okay, where's my flag? And I didn't put it here, obviously, because why would I create a payload which I actually call, right, and which I actually use? Thank you to Velez. Like, credit goes to you for finding that bug. Okay, now it's doing. Oh yeah, here we go. Here we go. Perfect. We brute forced like 16. The space of like 16 possible values for that nibble, and we got this one. So yeah, it was a really fun task where like we kind of showed how to play with ASLR by just overwriting the end of a return address and not the whole return address, and how to one of the ways which you can brute force a cookie if the cookie is constant. This is a requirement here. It does not work for random cookies because that way like it will always change. Even if you hit the correct value by accident, it would be a different one next time. So that's basically it for this task. Let's enter the problem, sorry, the flag. This is correct. Perfect, so we have it solved. Now, are there any questions? Let's see. Can a 64-bit CanaRy be bypassed? Yes, exactly the same method works. Again, the CanaRy needs to be constant. This happens on fork servers, and fork servers aren't that rare. So yeah, and there are different ways to bypass CanaRys as well. This isn't the only way. Can you recommend any good source for reversing cryptography? For example, using information that messages are variable size, possible keys, to narrow down possible ciphers. Okay. In Paged Out, there was one article about it from Kala, from Zeta2. You can look at this one, like identifying crypto functions, and Paged Out too. He has some ideas there. On the other hand, just look for identifying crypto functions and plus reverse engineering. I do not have any links at hand, but it is a known problem which has been approached from different angles many times, so there should be some information on the internet. That's all I can say from the top of my head. I know there are scripts and programs which try to identify ciphers in like binaries. That's a really good question, by the way. From Jorge, can you explain a little more about exit? Okay, I think I already did that. What if one of the bytes of the CanaRy is a new line? I already said that, but doesn't matter in this case. Why did I import subprocess? I imported it to call popen. Popen is basically like execute the program, executes this program, and I control standard input and standard output. On standard input, I pass it the payload. The string is being passed to standard input of the program, and then I get the standard output and standard error when the application finishes. Like that's how communicate work basically. Communicate is a pretty weird name. What it does is basically like execute and wait until it finishes. Yeah. So there we go. Okay, and we can close it. Now let's do one more task, I guess, today. So I do not need this one. I can close this and this. There's a forensics one, and Yeah, let's go. Oh, and a general skills one. I wrote you a song. Let's not go for songs. Let's go for the forensics one, and let's finish with this one. We recovered a binary and an image. See what you can make of it. There should be a flag somewhere. Perfect. Let's do it. When we are doing CTF, should we use subprocess or use spawnlib? Up to you. Absolutely up to you. Try both. Whichever you like. Because it's like, in the end on CTFs, it doesn't really matter which library you use to get the flag. It mattered which one was the fastest for you to use. It doesn't mean always the better one. It means the most convenient for you, where you feel the most comfortable with. So I feel more comfortable with using subprocess because I don't know pawnlib, I don't know pawn tools. If you know it, go for it. I didn't make a video about it because I never used it, seriously. I need to learn it someday. I know it's really good, I know a lot of people recommend it. I have some of my own similar scripts which I've written before it was created, that's why I don't use it, basically. Okay, so I downloaded the, whatever it's called, Investigative Reversing. Okay, and there's a PNG, and let's look at the PNG. Where'd the flag go? That's the PNG, and we have a binary. Let's see what the binary is. So yeah, let's look, and this is always the first step I do, is I look in like some kind of a file viewer, like text editor, doesn't matter. What I can see here already is an ELF, and it's for x86 64-bit Linux, so this is usually what I need. I usually also look for strings. The strings are flag.txt, mystery, no flag found. Please make sure this is run on the server. Mr. PNG is missing. Please run this on server. And okay. I do not fully understand the scenario here, but I guess we will figure it out in a second. I guess the idea is that we should not patch it. We should actually solve it some way. Sorry, what do we have here? Yeah, we have a flag. Okay, so we, even if we run it, like, I don't get it. This is not a SUID binary, so what do they expect us to do? Like, this binary doesn't have access to the flag challenge. It says permission denied. So how, what? I'm getting confused. Maybe they changed the idea. But yeah, I hope the flag is actually inside of it, and like inside of a PNG, and we can like find it somewhere. Let's take a look at the PNG as well, because why not? It looks like a pretty standard PNG, like pretty standard headers. IDAT is basically where the PNG data begins. And are there any funky stuff at the end? Yeah, at the end we have like this thing here which looks pretty funny. picoCTF, that means it's probably like, it looks like it's a little exort. Not every character is exort, but it's kinda somewhat exort. This should be, we know it should be F, right? And there might be some part missing here for some reasons. I'm not really sure what's that about. Maybe it's a red herring. We might figure it out when we start looking at the binary, which happens now. So I'm going to open it in IDA. Okay. So, okay, no flag found. Please make sure this is run on the server. Mystery PNG is missing, please. Okay, what does it do? It opens the flag for reading, it opens the flag for appending. Okay, so we are basically working, yeah, this is really a forensics challenge, basically. So this was run on the server, and we got the output, the result. And now we have a binary which created it, and the output, and we have to figure out what's the flag, what's the scenario, and now we can actually start playing with it. So, what does it do with, yeah, I guess this part is important. It basically grabs the like reads the flag, which is this size, I guess. Then it writes the first couple of characters directly at the end of a PNG. Then it grabs the next characters and it does something funky. It does like +5 to them. Then it does what, -3 here to it, and then it does the rest is the same. So yeah, we basically have to just correct a couple of bytes, I guess. And I'm going to make a copy of the PNG, and I'm going to open a hex editor. So we go to the end of a file. We go here. The first 6, let's actually, you know what? Let's do this, and let's do this. Here we go. Let's do it the other way around. Let's do this, and let's put IDA here. Oops, here we go. Okay, we go to the end. And, okay, first 6 characters, 1, 2, 3, 4, 5, 6, are the same. Now this is the 7th character. And what they do here is they actually add 5, so I'm going to decrement 4b by 5. I probably should do it with a script. Now I'm going to like, whatever. That's what, 11, right? So 11 minus 5 is 6, so that's 46. Then we have 80, and 80 minus 5 is 70b, because it's 16 minus 5. Yeah, but like even looks correctly. How many characters do we have to go through? We have to go through the 6th character. 14. You can see how advanced math I'm using. We have to go through 9 characters. Okay, B again, so that's 6. 6, 6, we did play with it. Then here, well, 30, that's an easy one. That's 10, which means it's 7, 5, that's an easy one. Here we go to 6E. Please correct me if I'm wrong. How many do we have? 6. Okay, so a couple of more. Then we have 64. Here we have 5F. And here we have 31. Okay, that's it. Then we have here -3, which means we have to add 3 here, so that's 74. Yeah, and it's just like, yeah, we can see the flag. Found it, and something, and that's it. That's the task, basically. Okay, that is correct. Task is solved. Perfect. Why not use WinCalc? Because I can do it in memory, I guess, and I'm too lazy to transcribe it. We could use the calc, we could use Python, we could write a script for it. It would be probably equally slow on all accounts. But whatever gets the flag in the end, and whatever you feel most comfortable with, I'm fine with just doing -5 in my head, even though I have to count from 6 to 14 on my fingers. Nice, and this is where we are going to, well, stop for today. We did solve only 4 tasks, I believe. That's still fine, I guess. It's not going super fast, but I guess we are playing with tasks which are a little bit harder. Well, okay, this wasn't hard, but most of the other tasks are probably going to be harder. So it's going to take us a couple of more streams to actually go through it. So I'm going to take a look if there are any other questions. If not, then we will call it a day or call it a stream. I do not see any questions. Are there any questions? No, I think there aren't. Okay, in normal condition, is the cookie random? Yeah, in normal conditions, the cookies are random. Every time you launch a process, then the cookie gets randomized, and it should be different for every thread. So if you leak a cookie from one thread, it should be different on another thread. That's on good implementations. And the randomness should be secure. You shouldn't be able to guess it. There are cases where you can guess it on some implementations, but usually you should not be able to guess it. Perfect. So that's it for today. Thank you to Foxtrot Charlie for being my moderator today. Thank you to everyone here for being with me, both on today's stream and on like this year, right? Because this is the last stream of the year. So we will see each other in January, I guess like the second week of January, unless something like prevents me from doing a stream. So that's it. Thank you for a great year. Happy holidays, happy new year, and see you next time. I'm going to leave you with some music.